Michael and Scott. And before we open it up for questions, I want to give them an opportunity to give a very brief statement to sort of put things in perspective with MRO and how it relates to the study of Mars. So, Michael?
Well, thanks, Dwayne. First, Rich, I want to thank you for a very concise, be able to fit all the spectacular results of MRO from its prime science mission into 1 hour is pretty amazing, revealing what's happened on the ancient surface and also some of the processes that are still going on today. One of the things I thought was pretty interesting, a nice segue, is that at the end of the video that was being shown while we're coming up here is the current landing sites that we have picked out for the Mars Science Laboratory. And so one of the other news items of today is that the naming of the Mars Science Laboratory has come out, and that's been done by a 6th grader, and the name is Curiosity. And so I think we'll be seeing some of that on the NASA TV throughout the day. Now what I'd like to do is turn this over to Scott Murchie, who is the principal investigator on the imaging spectrometer.
Thanks, Michael. So MRO is now into its extended science phase, and we've taken something like 13,000 high-resolution observations of the surface. And in the last hour, Dr. Zurich touched on some of the highlights. And looking back on it, what we've seen is really remarkable because we've seen a range of different kinds of rock formations that have different minerals in them formed by water. And that's telling us not only that Mars was wet in some places, but there were different kinds of water environments. And it's bringing up the question of habitability. There were places, as indicated by the minerals that we see in the rocks, where that water was dilute water, not too salty and not too acidic. And we're seeing signs that the kind of chemistry that was present in the water would have been compatible with the chemical processes that occur in life. And so it's really exciting to be part of MRO and to be taking all these high-resolution observations so we can begin to reconstruct the environment of ancient Mars and look for those places that offer the best hope of finding evidence for life on future landed missions.
Okay, so let's go ahead and open it up for question and answers. Now, when we have media briefings, we ask the media representatives to wait for the mic and give their name and affiliation. So we're going to do that here. We have folks within NASA, and we have some students in the audience and folks from other agencies. So when you get the mic, give your name, your school, or your organization, and please try to direct your question to either Rich, Michael, or Scott. And we'll take the first question there.
Okay, I'm Ramon DePaul, the program executive for the MRO mission. Richard, why this scientific endeavor of exploring Mars of MRO, why is this so important to us? And how does this change our curiosity? Just like the name of MSL is now Curiosity, which makes us come to work every day, makes us go to school every day, as the young girl wrote on her essay. How is this important to us, and how this changes our lives? How all this discovery? Can you explain that a little more? I know you discussed that some through the lecture, but I think I'd like to hear one more time, please.
Mars has been fascinating to us, I think, for 3 basic reasons. First, there's always been the question of life and whether Mars had life on its surface. 100 years ago, we were thinking that wasn't the question. There was life. The question was, how was Mars changing in terms of its climate? And that's the second question. It's different today, because today we know there aren't canals on the planet. We've seen the surface up close, but we still don't understand the details of how the Mars climate changed so dramatically and drastically over time, and what the implications are for life. So that's 2. Life, the question for life on Mars, and what that means for life in the solar system and elsewhere in the universe. And the second is that climate change, what caused that? The third reason, Mars is a destination potentially. It is a place where you could go and you could stand on the surface. You'll be in a spacesuit, but it is a place that a person could go and astronauts could explore in the way that they've done at the moon and the way we do in the high polar regions of the Earth.
Okay, I have an internet question here, and I believe this is for Michael. what is the cost of the Mars Reconnaissance Orbiter and the next step for the Mars program itself?
If I remember, MRO cost about $575 million through development. So that's kind of how much it costs to build and launch. And the operations, as we saw from Rich's talk, are fairly complicated, in which the spacecraft has to turn and point and taking pictures at several different scales. So the operations are kind of high in that they run about $35 million a year.
Okay. We have a young gentleman here. I believe he raised his hand. You give your name and your school, please.
My name is Nosakere, and I'm homeschooled. Rich, when you said follow the water, did you mean follow it back to its origin, or when or where is it going? It's going?
Yeah, that term covers a lot of territory, doesn't it? In some cases, it does mean follow it back to the source. Like when we talk about the gullies, where might it have come from? Did it come from an underground aquifer? Did it rain on the planet? In other cases, we're actually talking about following it through time. Back in history, when was it on the surface of the planet? And where did it go? Did it get frozen into the surface? Was it lost to space? How has Mars changed over time? And that's our other meaning to follow the water.
Okay. Two-part question. Second part. What method do you use to find where the water is going or where its origin was? By aerial orbiter or from the ground?
You do both from the ground and from orbit. From orbit, what we do is we look for the physical evidence that would be left behind by the presence of water. So Scott was talking about the minerals that were formed in water. And by looking for those specific minerals, we know that water was there. And something about the conditions, that is, was it acidic? Was it more basic? What was the nature of the water? Did it have a lot of salts in it, for instance? And so that's the way we look for it from orbit. We've also tried looking more directly by looking for liquid water beneath the surface with our radar. If there were a pool of water that was extensive enough, our radar ought to see a very dramatic change in the return from that interface of rock to water. We haven't seen that yet. It's possible that the liquid water today is much deeper on the planet than our radars are probing.
And you mentioned, Rich, seeing, looking on the surface, and part of that is why we send a rover, because there you can look at a very specific rock and do the analysis. And this is what the Mars Exploration Rover, Spirit and Opportunity, have done, and actually found evidence for water and the minerals that they find in a piece of rock that they're looking at.
Did you have another question? Okay. I've got two internet questions, and then we have another question here. First, for Michael, could you give a little more detail on the Mars Science Laboratory, or Curiosity, and what it will do and how it is different from the rover Spirit and Opportunity that are up there? And then I have another question for all three of you all. So, Michael?
Yeah, the Mars Science Laboratory is a very capable rover and is going to be carrying approximately 10 times the instrument mass to the surface that either Spirit or Opportunity doing. So Curiosity is a very capable rover, and I actually consider it kind of the first astrobiology mission to Mars since Viking, because it's going to be able to measure organics. With the ability to rove, it can go to different rocks and actually look where there might be what we call reduced carbon. And that sort of thing would give us an idea of what Mars has been like, and might even give us a clue about whether or not what the prebiotic planet might have been like, whether or not what organics are present, and maybe even biosignatures of life. Also, it's very capable in other instruments. A good example is what we call a X-ray diffractometer. And what this does is it's sort of the state-of-the-art of how you determine minerals. Minerals are very important because it gives you an idea of what has happened to a particular rock through time by looking at what minerals are present in it. So that mission is very capable and can actually explore for an extended period of time and give us an idea of really what the history on Mars has been like. And one of the